Greetings everyone. My name is Aditya Sharma, and this is fundamentals of compressible flow being conducted by NPTEL, right? And we are into the 12th live tutorial session of this particular course, right? Uh, we have been conducting such sessions from Jan onwards, right? From the very beginning of this course. And today's agenda will be measurement, diagnostics, and experimental facilities for the compressible flow. So it's just an extension of the previous week's content, right? So this is also the last in terms of if we see the weeks number of weeks of allotted for this course. So there are it's a 12-week course, right? So uh, in that series, this is the last session. But other than that, we have a concluding session on 17th, I believe, right? 17th of this month. Right? So the instructor for the course is Professor Niranjan Sahu, right? He is affiliated to Department of Mechanical Engineering, IIT Guwahati, and I am also uh, affiliated to IIT Guwahati at present. I am a research scholar here. I work uh, in the gas dynamics laboratory of Department of Mechanical Engineering. So we shall start today's sessions. Today's session in another 5 minutes. Thank you. So I believe we can start today's session, right? So as I have already mentioned, so we shall be discussing measurement diagnostics and experimental facilities for compressible. So mostly in these lectures, we will be focusing on high enthalpy impulse tests, right? And facilities linked to such flows. So the session goes like this. First of all, we discuss the topics that have been covered in uh, the this week's lectures, okay, of the current week's lectures, and after that we move on to the conceptual type questions, right? And after that, at last, we discuss numerical type questions, right? And with that, we conclude the session. So we shall move ahead in this manner only for this session also. Right? So, so let's see. So this is week 12. The first lecture in this week is lecture number 29. And the first topic here is aerodynamic test facilities. So what has been done in this lecture is firstly the compressible flow regimes have been discussed, right? So the four regimes have been mentioned. Right? So be it subsonic flow, that is for Mach 0.3 to 0.8, uh, or transonic flow, which is Mach 0.8 to 1.2, right? Then there is supersonic flow, for which Mach is greater than 1.2, and then at last we have hypersonic flows, for which Mach is greater than 5. Then there is classification also in terms of hypervelocity flow, where the velocity is in the range of 8 kilometer per second, right? Or if some object has a velocity equivalent to the escape velocity, right? When the object is on Earth, that is 11.2 kilometer per second. So in this range, if some object has a velocity, then that comes in hypervelocity force. So these all things, sorry. So these all things have been discussed in this first heading of this lecture, hypersonic velocity flows. So further discussion on hyper velocity flows has also been done. Right? So if we wish to simulate these high speed or high enthalpy flows, in that case, what is the energy requirement, right? Or what is the power requirement? So the estimate of that has been also discussed in one of the slides under aerodynamic test facility. So this rate of energy flow is rate of energy flow is given as half of rho A U Q A, where rho is the density of the flow rate, and A is the area of the slug, right, or the tube in which we have a flow, and U is the velocity of the that flow. So using this estimates have been presented in the lectures. In this sorry, in this lecture. So after that, the next topic is supersonic wind turbine. So we have discussed in, I believe, previous week's lectures. In one of the previous week's lectures. So what is the structure of a supersonic wind tunnel? Right? What are its various components? Right? So it has a reservoir, then it has a throat, right? Supersonic throat. After that, we have the test section for this supersonic tunnel, right? And at the end, we have a supersonic diffuser. It will slow down the flow with minimum pressure losses. So this has been again discussed in this lecture. After that, schematics, two schematics, difference with the schematics of uh, different setups, right? Different wind tunnels have been given. So first one is an intermittent in-draft tunnel. Right? The different components of it have been mentioned. So it's a supersonic type wind tunnel. And after that, we have supersonic slash hypersonic wind tunnels. Supersonic slash hypersonic wind tunnel. Right? So again, its schematic has been discussed. So after that, we moved on to high enthalpy impulse test facility. So I have earlier mentioned that this topic remains the thrust of this week's discussions. So, in this topic, the different setups have been discussed in this topic, right? So, but before that, firstly, there is this rate of energy flow requirement, right? So when we are simulating some speed, so in that case, what is the energy flow requirement? That has been mentioned. So which is nothing but this formula that I have written, right? So this formula caters to that, right? After that, there is one more parameter that is flow establishment time, right? So, be established. So here L is the length of the slug in which we are having a flow or we are simulating a flow, and U is the as is with the previous of the case in the rate of energy flow. So use the velocity of that. So this way the flow establishment time can be calculated. After that, discussion has been done on the uh, body pass ratio, right? BP, which is the ratio of time taken to so this is the ratio of the test time available in the facility, right? To the flow establishment time. So for attached flows, this falls in the range of 3 to 4, and then for separated flows, this falls in the range of 20 to 50. And after that, uh, a comparison between a wind tunnel and a shock tunnel have been done. So one major difference is that the wind tunnel is used to simulate low enthalpy conditions, and then shock tunnel is used to simulate moderate and high enthalpy flows. Okay, so in the high enthalpy impulse test facilities, the first setup that has been discussed is a shock tunnel. Uh, the components of a shock tunnel as are as follows. So first we have a driver section. After that we have a driven section, right? And at the exit of the driven section we have a CD nozzle, right? After CD nozzle we have a test section, and at last we have a dump tank. So I should draw the schematic when we discuss questions, right? Concepts based questions will be discussed. In that case, I should draw the schematic of the setup. For the time being, I'm just mentioning the components of the setup. And so this is a shock tunnel. After that, we have a Ludwig tunnel. So it has a storage tank, then it has a D-level nozzle, and after that it has a test section and a dump tank at the end. So the test time in this setup is of the order of milliseconds. The next in the setup is free piston shock tunnel. So it has a reservoir tube, and then it has a compression tube, right? Then it has a driven section. After that, it has a nozzle and then a test section. So in it, what we do is we use a piston, right, to compress some mono atomic driver gas, right, to attain high enthalpy flows, right. After this, we have uh, gun tunnels set up, right. So it is used to simulate hypersonic flow, right, which have high stagnation pressure and moderate stagnation enthalpy. Right? So its setup also we shall see later. Then at the end we have an expansion tunnel. So this expansion tunnel is used to simulate very high enthalpy flow, right? Such as hypervelocity flows we simulate using this setup. And the test time for this uh, setup remains of the order of microsecond, right? That is 10 raised to power minus 6. So previously we were in the previous setups we were seeing that the test time was in milliseconds, but in this case the test duration, right? The test time is of the order of microseconds. Then after that, measurement diagnostics of the setups have been discussed, right? So the measurement diagnostics has been discussed in the previous lecture, right? So setups like Schlieren apparatus, then shadow graph technique, then interferometer, then we have high speed imaging cameras, then there is electric discharge based flow visualization, right? So all all this has been discussed at the end of this lecture. Then in the next lecture, uh, discussion has been done on shock tubes. Right? So in the gas dynamics lab of IIT Guwahati, we have shock tubes. So we work on shock tubes. Right? So and this has been discussed. The shock tubes have been discussed in this last lecture. So after that, the lecture 31 is uh, in lecture 31. So professor has discussed the shock tubes that are present at our lab, right? So the instrumentations related to that have been discussed by the professor, right, from the lab only. So I had mentioned in the previous lecture that, or I had suggested that students must go through that video. So I again would repeat that. Right. So it gives a good idea that how things work in a laboratory environment. Right? So coming to this lecture, so we have first of all compressible flow theory has been discussed, right? So in it, oblique shocks have been mentioned, and then normal shocks have been mentioned, right? Then expansion fan has been mentioned. So all these things we have discussed previously, right? And then there is compressible flow when heat transfer is to be considered, right? Or friction is to be considered. So these things have been so we have revised these things in this compressible flow theory. After that, we come to the shock tube. Right? So shock tube is nothing but a tube-like structure, right? Where we have two sections. One is a driver section, and another one is driven section, right? And here we have a diaphragm. So what is done is the high pressure gas is given to the driver section, right? And the driver and driven sections are separated by a thin diaphragm, right? So diaphragm can be of aluminium or mylar sheet or some paper-based material. And as uh, we keep on pressurizing the driver section or filling the driver section with the high pressure gas, the time comes when this diaphragm bursts, right? So this diaphragm burst of diaphragm gives rise to a shock, right? And so this shock we use to perform our aerodynamic tests, right? So it's an impulsive test, right? So later in the lecture, it has also been mentioned that it is an impulsive device, right? So this is the basic structure of a shock tube. And then different data related to uh, shock tube has been presented, right, in this lecture. That comes in the characteristic features of a shock tube, right? After that, there is design of shock tube, right, where it has been mentioned that how we perform the structural analysis, right, of the material we are using for the shock tube. So in that case, we use the hoop stress, right? Sorry, to get the stresses involved in the material we are using for the shock tube. So this comes in the design of the shock tube, right? So after that comes the theory of the shock tube, where different ratios related to a shock tube have been given, right? So ratio of different regions. So in a shock tube, there are different regions have been defined, right? Based on the position of the normal shock, based on the position of the contact surface, right? Based on the position of the expansion fan. So all this has been given in the theory of shock. And then after that, the shock tube for the facility at IIT Guwahati. Sorry. So this has been discussed. So various parameters or specifications related to this shock tube uh, have been mentioned in the lecture. So at present, we have other than this shock tube discussed in the lecture, we have few other shock tubes we have in our lab. Right? So, and those shock tubes are of different specifications. Right? But this discussion gives a fair idea of the instrumentation and how a shock tube looks in reality. And then data related to this shock tube has been presented. And at the end, we have discussion on shock tunnel, right? So it has been mentioned that a shock tunnel can simulate max from 6 to 10, right? In the range of 6 to 10. And also it can cater to a Reynolds number uh, of 10 raised to power 6 and an enthalpy of 5 megajoule per kg. And for this shock tunnel, the test time remains in milliseconds. And the last heading is compressible flow and shock wave research. So various uh, uh, research that has been that is being done by researchers. So using these shock waves, right? So in different scenarios. So this has been discussed at the end of this lecture. So this was about the topics uh, of this week's lectures, right? So now what we will do is we will move on to our questions, right, for the session. So we have our first question. So it's on compressible flow regimes. It's a very basic question as far as the compressible flows are concerned. So the question number one, it says that which of the following is correct about the Mach number of transonic flows? So first option gives a range and then second option gives a range. Then the third option again gives some Mach, right? And same is with the last option. So if you see the number 0.3, so if some Mach value is below this number, so we consider that flow to be incompressible. And after this point is crossed, the flow starts becoming compressible, right? Or the compressibility cannot be ignored uh, in this case. So if you see all the options are for compressible flow zone, because everything here is greater than 0.3. Option A is for compressible flow, right? Option B is also for compressible flow. Option C is for compressible flow, but we also know that Mach greater than 1.2 is a supersonic flow, right? So, so this is not our option. Then Mach greater than 5, we know is hypersonic flows. Right? So this is also not our option. But then if you see option B, right? So this is from 0.8 to 1.2. So this is a region where the flow is transitioning from subsonic to supersonic. So this becomes a special field of study, right? The transitioning zone from subsonic to supersonic flows, and the range for this is considered to be from 0.8 to 1.2. Right? So in that case, option B is correct. Right? So this is a this is a transonic. Transonic, and this is so option B is correct. Let's see the next question. So next question is on aerodynamic test facilities. And the question says that shock tunnels are used to study dash flows. So the question is on shock tunnels, right? And we have 4 options here. So we have supersonic, we have hypersonic, we have hypervelocity, and then the last option is None of the above. So if you see a shock tunnel, I'm just drawing a schematic of the shock tunnel. So this is our driver section. This is our driven section. This is our CD nozzle. This is our test section. And this is our dump tank. So there are two diaphragms are used in a shock. One is here, and then the second one used is here. This is diaphragm one. This is diaphragm two. So what happens is we pressurize the driver section with the high pressure gas, right? It leads to the burst of diaphragm one, right? Or the rupture of diaphragm one. So this blast leads to a shock wave, right? Sorry. And then the shock wave from this reaches the second diaphragm, right? And then this diaphragm bursts, right? And then the flow travels in the CD nozzle, right? and from there it reaches or it enters the test section, right, where we have our models, aerodynamic models for study. And at the end of the this setup, right, or at the exit of that test section, we have a dump tank, right? So uh, we dump the gas, right, we have used in the driver section, the gas we have used, so we dump it here, right? So in this dump, we create a vacuum using some a vacuum pump, and such facilities are used to study hypersonic flows. So this is the setup of a shock. And the answer to this question is B option. Now moving on to next question. So the next question again is on aerodynamic test facilities. Right? And the question says that the question number 3. So it says that expansion tunnels are used to study dash flows. And the options we have are: first one is transonic, second one is supersonic, third one is hypersonic, and the fourth one is hypervelocity flows. So let's see the setup of expansion tunnel first, and then we shall answer this question. So the setup goes like this. So at first we have a reservoir tube, right? After that, we have a piston, right, to compress the gas in the compression tube. After that, we have a diaphragm that separates the uh, compression tube and the driven tube, right. After that, we have a secondary diaphragm, right, that is diaphragm 2. So this diaphragm separates the driven tube and the acceleration tube, right. And this acceleration tubes opens at a nozzle, right, a divergent nozzle. And at the exit of this nozzle, we have a test section. So here also we have two diaphragms. So in shock tunnels, uh, we also have two diaphragms. So same is the case, but the setup, how the two setups are different, so we can see through these two schematics, right? Schematic diagrams. So in shock tunnel, we were having a CD nozzle, right? And then there were two sections only. One was driver section, and one was driven section. But it has this compression tube, right? Because we are using a piston here, right? So that moves using a this reservoir pressure, right? And then we have uh, yes, so in the shock tunnel we were calling it a driver section, but here we call it a compression tube because we are using a piston, right? And then we have two diaphragms, right? And in the shock tunnel we were using a CD nozzle, but here we are using a divergent nozzle only. So this setup is used to study. It's right here, supersonic. Lights, it's right here, hypervelocity. So if we see our options, so option D is hypervelocity. Okay, so we have completed three questions, conceptual questions, right? So now we shall take a 5 minutes break. After that, we shall continue with the session, right? Because we are into already, so we have 1 hour has passed since this session, so we shall take a 5 minutes break and then we shall continue with our session. Thank you. Okay, so let's continue with the session. So the next question is on supersonic wind tunnel. So the question says that which of the following is not a component of a supersonic wind tunnel? And the options are as follows. So we have a D-level nozzle, and then we have a diffuser, we have then the storage tank, and then the last option is none of the above. So, so if we see a supersonic wind tunnel, so let's draw the schematic of it. There. So this is our reservoir. This is our CD nozzle. This is our test section. This is our diffuser. From here to here, this is diffuser, and from here to here is test section. From here to here is CD nozzle, and then here is reservoir. Right. So from the reservoir, we take the gas, right, or air, and then this expands in CD nozzle, right. After that expansion, it enters the supersonic, sorry, the test section, and then uh, after passing through the test section, it slows down in the supersonic diffuser, right? So this is a supersonic filter. And if we see the options, so D-level nozzle, if you see, essentially is CD nozzle, and then there is a diffuser and supersonic filter, right? And if you see storage tank, so the reservoir I have mentioned in the schematic is uh, can be called storage tank also, and then so there is no such option in which that is not a component of the supersonic filter. So option B would be the correct option. So a mistake I didn't see, but the option would be D here. Right. So this is our question number 4. Now moving on to next question. So, so today we have a couple of questions on high enthalpy pulse test facilities. Right. In that series, this is the first question. So question number 5, it says that the power requirement in aerodynamic tests increases as square of velocity. So whether this is true or false. So see, this is question number 5. Right? So first we know that kinetic energy is written as half of mv square. Right? And if we have to simulate a high enthalpy flow in uh, a laboratory scale environment, so in that case, if we are using some tube, right, or slug for that matter, so and the length of that slug is L, let's say, right? So we know that mass is equals to density into volume, right? And volume can be written as area into length, where A is the area of the slug and L is the length of the slug. So kinetic energy becomes half of rho A L V square. Right? And if we wish to calculate the power, so we will divide both sides by time, right? And this L by T can be written as V, right? So our power requirement becomes half of rho A V Q. So we have power requirement that depends on velocity, right? And it depends in such a way that the relation with power and the velocity is of cube factor, right? So if we see the question, it says that the power requirement in aerodynamic tests increases as square of velocity. So here it has to be not square but cube of velocity, right? So this statement is false. Right? So let's see the next question. Next question is again on high enthalpy impulse test facilities, and it says that the real gas effects become prominent in wind tunnels as specific heat ratio varies in terms of both temperature and pressure due to association of chemical reactions. So this question is about wind tunnels, right? So it says that the real gas effects become prominent in wind tunnels, right? Because gamma varies in wind tunnels, right? Because the chemical reactions are in picture in case of wind tunnel. But if we see the comparison between wind tunnels and shock tunnels that we have done in the lectures. So we see that the perfect gas model applies right here, as the gamma is either constant or it's a function of temperature only. So in case of wind tunnels, perfect gas model applies. But for the shock tunnels, this real gas effects are prominent because gamma varies in terms of both temperature and pressure, right? Because chemical reactions are linked to it. So for this question, the answer will be false, right? But then if we see the differences between a wind tunnel and shock tunnel, right? So power requirement in case of a wind tunnel is very high in comparison to a shock tunnel. Where in shock tunnel we have to burst two diaphragms, right? If you see a shock tunnel, so we have two diaphragms that we need to burst. But if you see a wind tunnel, right? in that case, we need a reservoir or storage tank. So store gas or air in it, so it requires a lot of energy. So power requirements in case of if internal is high compared to short term. Also in a wind tunnel, we don't see any uh, chemical reaction happening. Right? So these are the differences between a wind tunnel and the shock tunnel. So as far as this statement is concerned, so this statement is for actually for shock tunnel, but because I have just switched uh, the shock tunnel with the wind tunnel, so this becomes a false statement. Okay, so next question, question number 7. It says that it's also on high enthalpy impulse test facilities. So it says that a driver section and a driven section are the key components of a Ludwig tunnel. So whether this statement is true or false. So here we have a storage tank. Here we have a wall. Okay. Then this is a nozzle. And this is a test section. After that, we have a dump tank. So in the storage tank, we store high pressure gas, right? And then there is a valve, right? It's a fast acting valve, right? So we can just open it uh, very quickly, right? This valve, and then from this valve, the flow enters into the nozzle, right? And then this established high enthalpy flow. This enters the test section, right? And after that, the flow is dumped in a dump tank. Right? So if you see the schematic of a shock tunnel, so there also we have used a dump tank. Right? Now, if we see the question, so a driver section and a driven section are the key components of a Ludwig tunnel. So whether this statement is true or false. So because Ludwig tunnel has a this storage tube, right? Has a storage tube or storage tank, right? And then it has no driver or a driven section as such, and the storage tank, the gas from the storage tank leaves it in the nozzle, right? In the CD nozzle. So there is no driver or a driven section in our Ludwig tunnel. So this statement is a false statement. So let's move on to the next question. So the question is based on high enthalpy impulse test facilities. And the question says that a gun tunnel is used to produce hypersonic flows having high stagnation pressure and moderate stagnation enthalpy. So whether this statement is true or false. So first I'll draw this gun tunnel. Gun tunnel setup. So gun tunnel has a driver tube, right? And then it has a piston. After that, it has a driven tube. Then it has a nozzle. Then it has a test section. Here also we have a diaphragm. So we have a driver tube, right, in which the piston moves, right, and then we have a this driven tube. Right? After that, we have this diaphragm, right, and after that we have a divergent nozzle, which opens in a test section. So this setup is used for hypersonic flows, right? Then after gun tunnel, the question, this is question number 8, right? So gun tunnel used to produce hypersonic flow having high stagnation pressure and moderate stagnation enthalpy. So this is a true statement. Now, if you see question number 9, again on high enthalpy impulse test facilities, it says that in an expansion tunnel, an unsteady expansion gets propagated downstream of the secondary diaphragm location, which enhances the total pressure and total enthalpy of the shock heated test gas. So this is about the expansion tunnel. So we have discussed. So this is expansion tunnel. So if you see this expansion tunnel, right? So this is our secondary diaphragm, right? So this is asking the question asks about the test gas, right? So which is in this region, right? Which is in this region. So when the question says that in an expansion tunnel and steady expansion, sorry, gets propagated downstream. So this word is problematic, right? So it doesn't propagate downstream, but it gets propagated upstream. That is also the case for shock tube also. Right? So in shock tubes also, when the diaphragm ruptures, we see expansion fan upstream of the diaphragm. So this is a false statement. So this question now is on shock tube. So shock tube, the question says that question number 10, it says that the shock tube is an impulsive device to create short duration force and heat loads. So whether this is true or false. So if you see the schematic of a shock tube, I have already drawn it. Right? So in it we have a driver section and then we have a driven section, and these two sections are separated by a diaphragm, right? And then what we do is we provide this driver section with some gas. Right? And this gas ruptures this diaphragm, and which leads to formation of a shock wave, right? So when the question says that a shock tube is an impulsive device to create short duration forces and heat loads. So this is a true statement here. Because the test duration in these shock tubes is of the order of milliseconds. And the loads that an aerodynamic model that is mounted in a shock tube uh, receives, right? So this is also impulsive in nature, right? And of very short duration. Uh, Aerodynamic models are mounted like this here, right? And the loads this model receives are then taken using the proper instrumentation that has been mentioned or elaborated in lecture 31, right? So please see that video. So this is a true statement. Then next question is a numerical type question based on shock tube. And it says that in a shock tube experiment, nitrogen at 288 Kelvin is used as driver gas. Right? So in this shock tube, we are using nitrogen, right? From the storage tank, we are using nitrogen, or from the cylinder, we are using storage cylinder. We are using nitrogen as a driver gas, and the uh, gas we are using is at 288 kelvins, right? And two pressure sensors have been mounted in the driven section. And as the diaphragm ruptures, right? So a shock wave propagates in the driven section, and the interval this shock wave takes to travel from one pressure sensor to another pressure sensor is 0.513 milliseconds, right? And the distance between these two sensors is zero point 0.3 meters. So we see this. So let's say we have mounted two pressure sensors here, and we are acquiring the data somehow here from our data acquisition system, right? So distance between these two pressure sensors is 0 0.3 meters, right? And the time taken is this. So if we work this out, question number 11, solution. So velocity is distance upon time. that is 0.3 divided by 0.513, which comes out as 584.79 meter per second. And because the temperature given is 288, right? So if you calculate the speed of sun, so this comes out as now we know that Mach is velocity by speed of sun. So it comes out to be 580, 584.79 divided by 346.04. So this is 1.69. So you see the answer. So our answer also falls in this region. So the last question now we have for this session. Question is on aerodynamic test facilities, and the question says that if the velocity to be achieved for an aerodynamic test is 2000 meter per second and the length of the slug is 2 meter, find the flow establishment time in millisecond of the facility. So this is very simple. Establishment time we have learned is, this is question number 12 solution. The establishment is length by time rate. Length is 2 meter, sorry, length by velocity. First is 2000 meter per second, so it comes out to be 0.001 second, okay, which is 1 millisecond. So the answer to this question is 1 millisecond. So if you see the answer, this is 1 millisecond only. Right. So this way we have come to the end of this session. Right. So in conclusion, we'll say that we first discussed the topics related to week 12, and then we discussed few conceptual questions, right? 10 conceptual questions, out of which 5 were on high enthalpy impulse test facilities, right? Then we had few questions, one question on shock tube, right? After that, we moved on to numerical type questions, right? We saw one question on shock tube, right? And one question, numerical question was on flow establishment time, right? And this way we came to an end to the session. All right. So I'll end this session here only. Thank you, and we shall also have a, as I have mentioned in the beginning of the session, so we shall have a concluding session last, that will be the last session, right? On 17th. And the timing, if I remember it correctly, is from 10 a.m. to 11 a.m. on 17th. So it will be a 1 hour concluding session. So we shall see how it goes, right? So for the time being, I'll say thank you and happy learning, right? All right.